Hello, my name is Mark Van Kooteren, and today I'm going to be comparing linear regression and neural networks. So the main idea is that neural networks are kind of a branch of AI that's exploded in the past, few years. It's kind of a way to discover a relationship between variables. That's how we'll be using it. And linear regression has already kind of been used to do something similar since like the early 19th century. And on a sample data set that we choose, which one's kind of better and explain the differences. So we'll start with linear regression because that's the simpler one. It's basically the use of mathematical models to estimate the relationship between a response variable and one or more explanatory variables. One of the explanatory variables has to be categorical and discrete usually. It can have categorical variables and a whole bunch of other stuff, but we'll get to that. The kind of main idea behind it is there's some like relationship between the variables, which we can estimate by minimizing the residuals, which is to say minimizing the difference between what we would predict using the equation and what it actually is. And it's widely used in the field of statistics. Nearly every basic stats class covers it, at least a little bit. And yeah, I think we all know what linear regression is. Neural networks, they're an attempt to replicate the human brain. They're made up of like nodes called neurons that connect to different layers, with the connections being represented by a number which is called a weight, which is how strong the connection is. And each node is called a neuron, and then it kind of maps the relationship between our input variable and our response. The layer that we feed the data into is called the input, which is marked in red, and what gives our result or our decision is the output, which is green. As the problem gets more complex, you need more like layers in between them. So we have what we call a hidden layer, which we can choose how many hidden layers we have and how many hidden layers are in each node. So usually the more complex a problem gets, the more hidden layers we need, to kind of simulate the part of our problem is the bigger brain you need, kind of. And in this example, it's kind of like there are general rules as to how like much you need. It's kind of a thing we just have to like try a few and map it out. The best way I found is just try multiple different configurations, run it a few times, see which ones give you the best one. And for this example, I use five neurons in one hidden layer. It just seemed to work the best. So yeah. The data that we'll be using, it's 1,380 insurance claims with the amount charged, the age of the patient, the sex of the patient, the number of children the patient has, the BMI, and whether the patient was a smoker or not. When I found this data set, I just thought it was a nice data set on Kaggle that fit our needs. There didn't seem to be anything special about it. What I later learned when writing this paper, I discovered that it was originally from a book called Machine Learning with R by Brent Lars. I think I pronounced that wrong. But I hadn't read it at the time of writing. He focuses way deeper on regression than I went to, so I highly recommend it if you want to. But at the time of doing this, I hadn't read it. That's just something to be clear. So the first thing we need to do for linear regression is check our assumptions. There are 4 assumptions for linear regression where the errors are residuals. So the expected value of the residuals is 0. That's to say the mean is 0. The variance of it is constant, so it's just some constant number. It doesn't change as we go up or down. We have to make sure that the errors are normal or sufficiently normal and that the errors are independent. And the best way to do this is to just make a 4-in-1 residual plot, which I'll show in a moment. So here's our 4-in-1 residual plot. The normal probability plot and the histogram show which that whether that's normal or not. And as you can see, it's definitely like we have something going on with the normality assumption that's kind of bad. And the versus fit, that checks if there's any like constant variation, if there's any pattern. There could be one, there could be not. It's something you kind of have to eyeball. We could like check more, like mess with these more, but I didn't want to go like to waste too much time on linear regression when I was want to talk about neural networks too. And the versus order, that checks whether the errors are independent. Yeah. So since we ran the model, we're just gonna check it out first anyway. So when you first ran it with every single thing, every single variable, we found that the p-value for the sex of the patient and the region in which the patient was located, north, west, southeast, I think, it didn't those weren't significant. They were above our 0.05, our standard 0.05 for reject. So we got rid of those pretty much. And this was our new model in which everything was significant. So yeah, as you can see, everything is significant. So, we're good with very significant because the p-values are very low. And now we'll take a look at the coefficients. So now the coefficients, as you can see, I was going to use the actual equation, but it wouldn't come out the way I wanted to in Minitab, so I just use this. So as you can see, there's nothing scary with the VIF, and these are the coefficients. And the R squared for this model, it was 74.97, which means that about 75% of the variation in the data is explained by our variables. This is kind of good, but there are ways that we can improve it. So there are a few different ways that we can improve a model. Is the standard ones are, you want to look for any polynomial models we can do, or any transformations, which it's not that hard to do. We can look for any interactions between the variables, which is again not that hard to do. Or you could collect more data, which is always time and money. So most of the time you try the first two. For this paper, I'll only do the first one just because I didn't want to spend too much time on doing the regression example. And how we check for like any polynomial models is we run a scatter plot between the values and what to check for polynomial models, we check the quantitative variables versus the actual response variable. I'll show an example here. And we look for any like pattern or curve. So there's an example of one where for charge versus BMI, there might be a pattern, there might not. It's something kind of weird. I didn't put too much. I didn't want to focus on this too much, so I just decided to ignore it. But with scatter plot of charges versus age, you can kind of see there's obviously some kind of curve. So what I ended up electing to do was I put an age squared term in the model to see how that improves. And when we ran that model, sex and region again dropped out of our equation. So this was our table. And something of note is normally under normal circumstances, we would get rid of age because it has the p-value above 0.05. But because we have a polynomial of a higher power, we can't get rid of it. One of the rules is if you have x squared, you found something for x squared, you can't get rid of x. So we'll keep age in our model. And this is what our equations look like for smoker versus non-smoker. And here the R squared was 75.25. So it went a little bit up. That was nice, but we could improve this a lot more. We could go a lot more deeper into this, do a whole bunch of fancy transformations. If this were a presentation about regression specifically, I would, but I also want to talk about neural networks. So we're going to move on. So that you could make this a lot better, but we won't here just for time. So for our neural network specifically, we're going to be using what's called supervised learning, where the data is in pairs, our inputs, our desired output, and our inputs. And we kind of want to learn about the relationship between the inputs and the outputs, like regression. So the first thing we do is we could feed all the data into the model, but then we'd really have no way of testing it. We'd have no way of seeing how good it is. So what we do is we split it into a certain port that we allocate for testing and a certain port we allocate for training. And for me, what I use is just an 80-10 split. It seemed to work pretty well. And another very important thing with working with neural network is to normalize your data in some way. If you don't do this, some variables have a bigger effect than others. Your error will be massive. You'll have really weird errors. One common thing that I went to before I normalized was the neural network would output the same number every time, which was weird. So you definitely want to normalize your data before. And there's a few different ways of doing this. The way that I opted to do was using the min-max normalization, where you take the specific data point, subtract away the minimum, and then divide by the range or the max minus the min. The actual code that was used to do this, I found when I was trying to figure out why it wasn't working. I copy pasted that from a tutorial online, and it's marked in the code. So that's something important. So yeah, it is marked and it's in the works cited. So yeah, when we split into our data, the actual code wasn't that hard using neural networks. There's a few stuff I did to make it better, but so we have 5 hit. As you can see, we have our inputs. The different variables, those are just the sex2, smoke, and region 2. Those are just changing it to numerical variables because you can't put the quantitative variables into the neural network. So those are marked in those are marked in the code where I did what I did for those. And as you can see, we have a hidden layer of 5 node. We have one hidden layer with 5 nodes, and and to see what our results are, we use the neural network to predict the charge of our test data. So we give it all the variables and say, let it predict what it would be, and then compare to what the charges actually were. To actually do this, we unnormalized our data, which is just doing the exact opposite of what we did, which was also copy pasted. And then we take the actual price they were charged, then subtract what we predicted from it, and then take the absolute value of the mean of those values. It's kind of like a residual. And in the end, the average difference was 0.0017, which hey, is very accurate. So we've done a good job. Woo, high five. Okay, so that was our results from that. So in the end with regression versus neural networks, regression, it kind of depends on the data you have and the problem you want. Regression tends to need less data but has a higher overall error. So if you're only working with a few things, again, the neural network needs to have a whole bunch of data to actually be accurate. Neural networks are also harder to set up. Regression can be done in any statistical software, pretty much a simple regression. There's probably a million different things you could do better whenever you do a neural network, so no one knows everything. There's probably a lot of different things I could have done better here that I just didn't know about. So, but regression, any statistician could probably run a very good regression. Not every, statistician could run a very good neural network. A good thing about neural networks is they can constantly be fed more and more data. So as a website like Facebook is collecting more and more data, it could, feed more. It could, constantly improve the model. So that's one of the benefits. You don't have to run the regression and continuously. The neural networks, you can just kind of do it. There's also a little bit more randomness involved with the neural network because the test data is split. So you could end up getting a split that's biased one way or another. We hope that it's representative. As we always say in stats, the more data you have, the less impact it will have. So that's something we always say. But yeah. So in the end, if you have more data and you have if you have a lot of data and you have the experts who know how to do this, you always kind of want to do neural networks. If it's less data and you want it to be more simple, you could just do regression. And that is my works cited. And yeah, thank you for listening. Have a good day.